computer. Is that recording? Yes, it is. I have no idea if the microphone is picking anything up at all.
I can hear you perfectly fine,
Right,
Professor.
cool. Excellent. Thank you. All right. So it is. Okay. So my plan today. So first up, yeah, nice to meet you guys in person. To the extent possible, I'm going to be doing things in person. If I get sick again, we'll go back online. But generally what my plan is going to be is, because so many people are going to be in and out, since this is sort of the season of illness anyway, I'm going to try to record my lectures in here. I'm going to keep producing. If you don't want to look at this, because you don't want to look at a classroom lecture, I will keep producing at least the short videos, 25-minute videos covering what I do in a given class. Those will also continue to be posted on YouTube. If you guys need anything else, just let me know, right? I'm going to try to work around the fact that I'm expecting a lot of absences. Try to be here in person if you can, but don't come if you're sick, okay? There's a lot of ways to participate in the class. Yeah, so today what I want to do is I want to talk about, I want to finish up 11.2 and I want to answer questions from the homework. That's kind of like what my plan for the day is. So we're not going to have a quiz today, or sorry, no quiz Friday, no quiz tomorrow. And I haven't yet thought about what my solution to next Friday is, but as of right now, I'm expecting there to be a quiz in class on Friday next week. Okay? So we'll start Friday's lecture next week with a quiz. So, yeah. So before I get started here on the rest of 11.2, is there anything I can answer from 11.1? I've got some questions in the Slack channel that I answered already. Does anybody else have any questions about anything about the content of 11.1 or stuff we've talked about from 11.2 so far?
Can we do a homework problem for 11?
What's that?
Can we do a homework problem?
We can do a problem for 11. Yeah.
Okay, I asked about 18 yesterday. I just couldn't.
Okay, so 18 was.
This then is negative 2 to the power of n over 2n factorial.
Over 2n factorial. Okay, so this actually gives us a chance to talk about what 2n factorial actually means, right? The first thing. So if you don't see parentheses around the 2n, the way that you're supposed to interpret this is 2 times n factorial. Okay, it doesn't matter in this case, but that's how you're supposed to interpret this. Okay, so if you're looking at a sequence that's built out of terms that look like this, a good way of trying to analyze what's happening is just to write the sequence out and see if you believe where the answer is going. Okay, I'm not even going to simplify anything. I'm just going to write out some terms. So the idea here is, does this sequence converge or diverge, right? Okay, so let's just compute some terms. So A1 is minus 2 to the first over 2 times 1 factorial. I'm going to remind you guys real quick, I got a question about this. N factorial just means a list of numbers starting at 1, ending at n, and you just multiply them all together, right? So you're increasing by 1 each time. And where you stop is given by what's involved or what's inside the exclamation point. So the difference here is that if it was 2n factorial, the list would start at 1, and the last number in the list would be 2n instead. Okay, so those are different quantities, and you should interpret them differently. Okay, so A1 is negative 2 over 2 times 1 factorial, which is 2 times 1. And A2 is minus 2 squared. In fact, let's write it like this. Minus 2 times minus 2 over 2 times 1 times 2. And A3 is minus 2 times minus 2 times minus 2 over 2 times 1 times 2 times 3. So my question is, which of these is going to win in the end? This is a fraction. There's only a couple different things that can happen here. I mean, they're both running away to infinity. But what's going faster? So why is the bottom going faster? It'll only never increase, but the bottom will increase to infinity, so you're multiplying by higher and higher numbers. Yeah, so eventually what ends up happening, like way out in the sequence, like if you think about what happens with A100, say, the last number in this list on top is a negative 2. But the number on bottom is a 100 factorial, right? Like, you know, think of it like there's a 100 that gets thrown on the end. These things that you're multiplying by in each step are getting smaller and smaller and smaller and smaller. The denominator wins. So if the denominator wins. And when you have a limit, when the denominator wins, the limit is 0, right? The denominator is going to infinity faster than the numerator is. So now there's this order. So this is one of these things that maybe nobody has actually formally told you guys in the past, but there's an order of how powerful or how quickly things grow. So the slowest growth. So we're going to go from slowest growth to largest growth here. This is the usefulness class. So natural log of n is the slowest. Natural log grows incredibly slowly as n goes to infinity. What we're thinking here is as n tends to infinity. Log is really slow. And above natural log is anything that looks like x to the n. Let's get the x out of there and make it more clear. A to the n. Some constant to the nth power grows faster than any. In fact, let's do this first. First polynomials. So logs first, then polynomials. So polynomials are things that look like n to the p, where p is some fixed power. So for example, n squared, n cubed grows faster than n squared, n to the fourth grows faster than n to the third, and so on, right? These are, the powers are fixed, but the inside of the power, the base is changing. So this is called polynomial growth. And faster than any polynomial growth is exponential growth, where now instead of the base changing, the power increases instead. So if you had something like a to the n, this is called exponential growth. So exponentials grow faster than any polynomial. This is exponential because it's the repeated base to an increasing power. And the fastest of all, factorial growth. The factorials grow faster than anything. Okay. So this is sort of just a guideline to when you're looking at a limit of a fraction, you can usually guess what's going to happen just by comparing the order of growth of the pieces. So when I look at an here, I see something that grows exponentially over something that grows factorially. And exponential over factorial has to go to 0 because factorial grows faster than exponential does. Actually, probably the people who have seen this before, if you've done anything, there's whole chunks of computer science dedicated to analyzing things in terms of this kind of growth numbers. All right, does that answer your question? Any other questions from 11.1 I can answer? Yep. 19. Can you tell me what it is?
That's so limit is n goes to infinity, and then it's root n. And then under that root is.
All right, hold on, wait, 19, so you said an is root n.
Or sorry, it's n, the nth root.
The nth root.
Yeah.
Nth root of what?
Of 3 to the n plus 16.
Okay. The nth root of that. Okay, so when I'm looking at this thing, so again, before I do any computations at all, I'm going to try to guess what the answer is. Now, if you put this in Desmos or some other graphing utility, it's going to be very obvious that the answer to this question is 6. So if you plot this, and if you put it in Desmos, it won't show you the whole graph. You got to zoom out so you can see where the asymptote is. So if you go anywhere and you actually plot the function, if you plot f of x is equal to 3 to the x plus 6 to the x 1 over x. What that ends up looking like is it's got a branch that comes down and does, this branch kind of comes in and goes like this. And there's another branch that goes this way. And that line right there is at 6 for this particular function. And you might think, okay, why is that happening? So again, qualitative analysis before quantitative analysis. So when I look at this, I think when n gets huge, is 3 to the n or 6 to the n the big winner in that expression inside? It's gotta be 6 to the n, right? I mean, multiplied by 6 every time is way bigger than multiplying by 3 every time. So when n is very large, this looks like 6 to the n. So I would say for n large, this is on the order of 6 to the n over 1 to the n, because the 6 to the n dominates the 3 to the n. The 3 to the n is like meaningless if you put a billion. If you put a billion up in the power here, 3 to the billionth is so much smaller than 6 to the billionth. That's the 6 to the n is the winner. But what's 6 to the n to the 1 over n? 6. So that is not formal mathematics, but it's an intuitive way of guessing what should be happening. Okay. So now how do you actually do it formally? Well, you gotta take a limit. And you look at that and you say, okay, well, the inside of this chunk right here, that tends to infinity. And this chunk out here tends to 0. So this is infinity to the 0, which is an indeterminate form. And when we have indeterminate limits, the only tool we have is L'Hopital's rule. So this is a L'Hopital problem. So what we're going to do with it, it's that exponential form of L'Hopital's rule. So at some point you should have learned that when you have an indeterminate limit in exponential form, that the trick is to take the limit and rewrite it as e to the limit of g natural log of f. That's like the move. Is you use e and logarithm because they're inverse functions to algebraically manipulate this thing into this form. And then we're going to consider this limit instead. If you don't remember this, the basic idea is that if you have f to the g, that's the same as e to the natural log of f to the g, because e and log are inverse functions. So I'm kind of uncanceling an e and a log, specifically because the log rule says when I have a power, I can pull it out front of a log. So that's the whole point of the trick, is to use the fact that the log lets us drop powers out front. Okay. All right, so in our case, that's going to turn this function into e to the limit as n goes to infinity of 1 over n times the natural log of 3 to the n plus 6 to the n. And it's still indeterminate though, because now I've got, this is going to infinity, so this whole thing is going to infinity, but that's going to 0. I got 0 times infinity, indeterminate form. What's the fix? Still can't use L'Hopital because I have to have 0 over 0 or infinity over infinity. What's the fix here? Just rewrite it with the n on the bottom. This is e limit as n goes to infinity of the natural log of 3 to the n plus 6 to the n over n. And now it's in the correct form because the top goes to infinity and also the bottom goes to infinity. So this is infinity over infinity. I can L'Hopital it. This is infinity over infinity. And now you just need to remember what the derivative of the natural log of a bunch of crap is. Maybe you do. So that is equal to, by L'Hopital's rule, the limit, here, n goes to infinity of 1 over 3 to the n plus 6 to the n times the derivative of the denominator, which is natural log of 3 times 3 to the n plus natural log of 6 times 6 to the n over the derivative of the denominator, which is 1. And it's pretty easy to show that this limit is the natural log of 6. And the way you do it is you rewrite it as e to the limit of natural log of 3 times 3 to the n plus natural log of 6 times 6 to the n over 3 to the n plus 6 to the n. If you divide top and bottom of this by 6 to the n, so do 1 over 6 to the n, 1 over 6 to the n. That's a common trick in these type of things, is find the largest piece and divide everything by it. If you do that, what you end up with is the natural log of 3 times 3 over 6 to the n plus the natural log of 6, because 6 to the n over 6 to the n is 1. And on bottom, you get a natural log of 3, a natural log of 3. You just get 3 over 6 to the n plus 1. Forget this natural log of 3 for a second. That's a constant. Where does that go as n goes to infinity? 0. It's a fraction, right? 1/2 to the n goes to 0 as n goes to infinity. This goes to 0. Where does that go? 0. So that's what's left over, natural log of 6. And e to the natural log of 6 is 6. So the long-winded approach, formally, this is the sort of mathematically correct way of doing this, but notice that we got the answer just by thinking about orders of growth, right? And we could have done that directly by thinking about 6 to the n dominating the problem. Any questions about any of this stuff in here? Okay.
I have a question.
One thing I should say. Right,
Would you accept that kind of answer on the test if you just said like, if you consider like the order in which it's like placed?
unless I say formally answer the question, then the first answer would be acceptable, yes.
Okay, thank you.
Right? And that's actually the kind of thinking I want to encourage in here as well, right? Is that if you can come up with the answer, even if I didn't accept that as the full credit answer, that first order of growth thing that I wrote down, that's worth 80% of the answer at least, right? Because you thought about the order of growth and you computed the answer. Right? This is the way most people think about this stuff. You find the answer, and then if you have to go back and verify it, you can use the formal mathematics to do it. The other thing I want to say is, if we come across an idea here when I'm explaining something that you don't remember because you didn't take, say, Calc 2 last quarter, but you took it like 2 years ago, maybe there's somebody here that did that, and you need refreshers on any of these ideas, send me an email so I can put up in the Slack channel or something, like some supplementary guides to say maybe you don't remember local calc rules. Or, you know, I hope this is not the case, but if the step where I took the derivative of the natural log is confusing, right? That's going to be something, we're going to be doing this kind of analysis the whole quarter. So you got to be able to work with these things. All right, anything else on the homework I can answer before I go on? I got time for maybe one more. Yep. Number 15, which one was that one?
It's the limit and 1 plus 7 over n.
1 plus
The entire thing to n.
7 to the n.
1 plus 7 over 9, all of that to n.
Get over now.
Yeah.
Okay, that right there, I just automatically know that's some kind of e. Okay, so this is our 15. Okay, so this says the limit as n goes to infinity. I bet the answer is e to the 7th. That's my guess. 1 plus 7 over n to the n. Now, the reason why I would think that that would be exponential is because this is actually the definition of e. So one of the definitions of the number e that you're supposed to remember, maybe you remember, I don't know, that you should have seen before at some point, is that e is equal to the limit as n goes to infinity of 1 plus 1 over n. Yeah, that's one of the ways of defining what e is. Okay, this is the same as the last problem. It's the same problem. This is an exponential form, f to the g. As n goes to infinity, this goes to 1. As n tends to infinity, the inside of this tends to 1 because 7 over n goes to 0. And the exponent is tending to infinity, and that's also an indeterminate form. Because the 1 is trying to make it a 1, but the infinity is trying to turn it into infinity. So they're fighting each other, right? So you actually have to rewrite this as, so I'll say this is indeterminate. So you have to rewrite this as the limit as n goes to infinity of e to the, well, I'll just give you the boiled down form is the natural log of 1 plus 7 over n over 1 over n. That's what it turns out. And when you do that, when you rewrite the question in this way, what you end up with is the natural log of 1, which is 0, and something tending to 0 on the bottom. So now it's a 0 over 0 in determinate form, and you can use local calc rule on. So you gotta flex your natural log differentiating muscles here. So E, the derivative of the top is 1 over 1 plus 7 over n times the derivative of that, which is minus 7 over n squared. In the denominator, you get minus 1 over n squared. The derivative of 1 over n is minus 1 over n squared. Oh, there's a limit here. So, fortunately, I can algebraically cancel these 1 over n squared that are floating around. And so this becomes e to the limit as n goes to infinity of 7 times 1 over 1 plus 7 over n. The minus 1 over n squared on the top and the minus 1 over n squared on the bottom cancel. They leave a 7 behind. This limit is really easy to compute because it's just 1.
I'm just curious why would 1 to infinity indeterminate instead of just 1?
Okay, so it's indeterminate because these numbers are bigger than 1. You have 1 that you're starting with, and you're adding a little tiny bit to those 1s, right? So if that is not going to 1 fast enough, then the exponential can blow it up into infinity because numbers larger than 1, when you take their powers, they get bigger.
Okay, so it's because it's not exactly 1.
It's because it's not precisely 1. That's right. It's in the limit, it's 1, but it's 1 from above, right?
Okay.
These are growing, these are shrinking down to 1 from above. So the exponent up here wants those to be infinity because it says, oh, you're bigger than 1, I make you bigger, right? So that's kind of what's going on in the background. Yeah, it's not that it's precisely 1, it's that it's not precisely 1. It's a little bit bigger, but tending to 1. And the speed with which this is going to 1 and the speed that this is blowing up to infinity dictate what happens in an indeterminate form like this.
Okay.
Yeah, if this went to 1 fast enough, then the answer is 1. Like if there was an n squared down here, the answer would just be 1. All right, so let's finish up 11.2. You guys can finish your homework. All right, so 11.2. What have we not done? We did the geometric series. We did. Okay, so we're gonna do the test for divergence. That's a kind of a cool one. Oh, let's start with telescoping series. I know this comes up on the homework, right? In fact, I think it formally defines it for you. So the idea with a telescope here refers to the fact if you think about like a movie with a pirate in it, they take their telescope and they stretch it out like this and they collapse it back down again, like a sort of collapsible telescope. That's what's going on here with the name telescope. So I'm going to write down a series for you. It's not the mathematical trick that's used to hide it. Suppose I just give you the series an is 1 over n minus 1 over n plus 1. Perfectly legitimate series, or sorry, sequence. That's the sequence. To make it into a series, we're going to add these things up. So if I want to do a sum from n equals 1 to infinity of 1 over n minus 1 over n plus 1, the first thing I'm going to look at when I look at that is it a geometric series? And the answer is, sure won't look like one. Geometric series, remember, was things that look like this. I don't see that structure. The n is not up in the power. So you should always check first to see if you're looking at a geometric series. And if you don't see a power to the n, there's no way it can be geometric. So this is not geometric. At this point in the class, we have 2 tools: geometric series or writing a bunch of partial sum counts. So we're going to write down partial sums and see if that tells us what the answer should be here. So remember that the sequence of partial sums just means add the first couple of terms together. S3 means add the first 3 terms together. And if we keep doing that, eventually this thing should be equal to the limit as n goes to infinity of Sn. If this sequence has a limit, it's equal to that sum. So the sequence of partial sums tells you what the series adds up to. This is called the sequence of partial sums. And the big deal with infinite series is infinite series add up to a limit if the sequence of partial sums has a limit. Let's write that down. All right, so S1, all right, let me write down the formula for AN real quick. AN is equal to 1 over n minus 1 over n plus 1. So S1 is 1 over 1 minus 1 over 2. It's just A1. I have to be more clear here. S1 is A1, which is 1 over 1 minus 1 over 2. I take that formula, I put in a 1, and I get 1 over 1 minus 1 over 2. I'm not going to simplify anything. S2, and my voice is shot today, is A1 plus A2, which is 1 over 1 minus 1 over 2. There's A1 plus 1 over 2 minus 1 over 3. There's A2. And notice what happens is these overlap and have opposite signs. They cancel. 1 over 1 minus 1 over 3. S3 is A1 plus A2 plus A3. Cancel, cancel, and you end up with 1 over 1 minus 1 over 4. So this is what we mean by telescoping, right? The entire middle of the series just cancels out and leaves you with nothing but the first term and the last one. Okay, so I'm going to make the claim here that Sn is equal to 1 over 1 minus 1 over n plus 1. That's what it looks like to me. When I'm done doing the cancellation, the only thing that's left is the first term. I don't know why I keep writing 1 over 1. I know it's really 1. The first term, which is 1 over 1, minus whatever the last term of that particular partial sum was. Well, this was a 4 when n was equal to 3. This was a 3 when n was equal to 2. So the only thing that survives is the n plus 1 in the denominator. So that is a formula for the n partial sum. So if this is going to add up, it has to add up to the limit of that sequence. Limit then goes to infinity of 1 minus 1 over n plus 1. This is this thing right here. This is the limit as n goes to infinity of the sequence of partial sums, and that means it's equal to the sum of that infinite series. So this is convergent, and it converges to 1. So this is probably the most conceptually confusing thing in here, is that really there's no such thing as an infinite series. Really, there's a sequence of partial sums, and we're sort of covering that up when we write this down. But the basic object that's being considered here when we work directly is this object, the sequence of partial sums. This is the thing that dictates whether or not the series converges or not. Okay. So the move that we made here was we wrote down the infinite series, we turned it into a sequence of partial sums, we found a formula for Sn, and then we took the limit of that object. Okay. Any questions about that? I mean, I know this is weird. I know. Okay. If you're not comfortable with this, do some more examples. Right. So for those of you that have access to the book, there's a lot of examples of telescoping series in here. There's some in the homework as well, where you actually have to formally compute these things. Okay. So that is what I'm going to do with telescoping series right now, unless I have questions about it. It's okay? Yep. That's right. It could be the case that you're left with a couple of terms at the beginning, but the idea is as long as you can figure out a pattern for what's left behind, as long as there's a finite number of terms left, And it's always the same past a certain point. I mean, the idea is this worked because the form of what came out was always exactly the same and completely dependent on what index I was looking at, right? And the telescoping part just means we get rid of the infinite stuff in the middle, right? With this like potentially huge long list that grows and grows and grows, that's not there. There's the 2 terms left, so yes. Now, a series does not have to be telescoping in order to find a formula for Sn, right? I think I did an example in the other notes where we found a formula for Sn where I was looking at the sequence 1/2 plus 1/4 plus 1/8 plus 1/16. And then from that, I figured out that the sequence of partial sums was S1 was 1/2, and S2 was 3/4, and S3 was 7/8. And then from here, I wrote down the formula that Sn was equal to 2 to the n minus 1 over 2 to the n. You can still do this even if it's not telescoping. It just means, can you come up with some way of writing a formula down for Sn? And telescoping series are one of the ways that that happens. So when you're doing integral calculus, one of the things people tell you when you're learning integrals is, if you can't think of anything else to do on an integral, try to do it with integration by parts, right? It's your method of last resort, but oftentimes it just works, right? Oh, I don't know what to do. I'm just going to try to do it with parts. In the same way, when you're looking at a series, if you don't know what to do, start writing the partial sum. This is move 1. I have no idea what to do. There must be a way to solve the problem. Start writing the partial sum. Okay. So now we come to one of the most important ideas and one of the trickiest in the study of series, which is most series, we have no idea what they converge to, or even if they do. And we have to develop this crazy machinery to determine when that happens, because an enormous number of things that we study in mathematics and science turn out to be expressed in these sort of infinite quantities. And so let's look at this. Does that series converge or diverge? Why? This is a geometric series. I'll make it even more explicit. I can make it n minus 1. It's okay, right? The idea, I'm not trying to trick anybody. This is a geometric series, right? It's geometric because if you start to write down the terms, they look like they've got the ratio where you're multiplying the previous one by 1/2. So this is of the form a r to the n minus 1, r is less than 1 in absolute value. So it's a convergent geometric series. All right, what is this? Not a trick question. 0, right? 1/2 to the n is 0. So what you've just told me is, for this convergent series, the limit as n goes to infinity of an is 0. You just told me that. Here's a convergent series. The formula that defines the terms goes to 0 as n goes to infinity. These guys went to 0. What about this one? Here's the dumbest possible divergent series. That converge or diverge? Converge. Think about the partial sums here. 1. So this looks like 1 plus 2 factorial, which is 2, plus 6 plus 24, and so on, right? That can't possibly add up to anything except infinity, right? I mean, the terms are getting bigger and bigger and bigger. It has to, I mean, this must add up to infinity. It has to. This, I mean, this divergence. Each time you add on a new number, it gets bigger, like a lot bigger. So this is an increasing function. There's no way that this series can converge. And notice that the limit, as n goes to infinity, of n factorial, is not 0. Infinity. So what can we say about the relationship between an, the limit of an as n goes to infinity, and the convergence of the series? What if I just wrote down a generic series, the sum of an, and I tell you that the limit as n goes to infinity of an is not 0. What can you say? Has to diverge, right? If that doesn't go to 0, this has to diverge, has to, because these aren't getting smaller and smaller and smaller, and adding less and less and less. There can't be a horizontal asymptote. These are not getting smaller. So if I have a series, if the terms don't go to 0, then this diverges. Okay, if an converges, what can you say about this? Now I've got a convergent series. I'm starting out by telling you the series converges, like this series. It converged. What can we say about the limit of the terms? It better be 0. If it converged, this has to be 0. If these converge. It's one of the rules. As you keep going out in the series, the contributions to the terms have to get smaller and smaller. Otherwise, there's no horizontal asymptote. So if the series converges, then the limit of the terms is 0. All right, now here's the tricky question. What if? Here's a math professor question. True or false? If the limit as n goes to infinity of an is 0, then the sum from n equals 1 to infinity of an converges. Now notice, this is not the same as what we wrote over here. It's the converse. It's the backward statement. Here we said, if it converged, then the limit is 0. But what about if the limit is 0? It's true or false? How many people say true? How many people say false? Why? Okay, so that got some hands for false. So now I'm going to poll the field here. Put up your hand if you put your hand up for false. Okay. Why? Yeah. It feels like a trick question. So that is a very well refined sensitivity to the way math classrooms work. You have an example? There's a really famous one, which is what we're driving at here. I'm working my way forward.
Oh, yeah.
Yes, okay. So famously, and you must have this drilled into your head, famously, this is a false statement. Because the easiest series of all does not converge. The sum from n equals 1 to infinity of 1 over n diverges. So 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 and so on. That's a divergent series. The terms go to 0, but they don't go to 0 fast enough. This divergence. Much to the annoyance of basically every scientist that studied this when they built this stuff. Whole areas of mathematics have been built around trying to make this make sense as a convergent series. But it grows too fast. So this actually adds up to infinity, slowly. Okay, so what that means is we can use the terms to tell us when a series diverges, but we cannot use the terms to tell us when a sequence converges. If we know the limit of an is not 0, automatically the series diverges. But just because it goes to 0 means we know nothing. So this is a famous and useful, but very easily confused result called the test for divergence. And the test for divergence says, if the limit as n goes to infinity of an is not equal to 0, then the sum from n equals 1 to infinity of an diverges. And many a calculus 3 exam question has involved writing down some sort of absurd series that you have no idea how to do. But if you make the observation that the terms don't go to 0, you can just say diverges by test for divergence and move on to the next question. So, for example, let's look at the sum from n equals 1 to infinity of n factorial times 2 to the n over 3 to the n times the cosine of n. Man, that's nasty. Convergent or divergent? We're not going to do formal mathematics here. We're going to do orders of growth to try to analyze this. What's the largest growing term in this thing? Of all the pieces of this, what grows the fastest?
N factorial.
This n factorial right here grows the fastest. Is it in the numerator or denominator? Okay, so I got something going to infinity like a factorial, something going to infinity like an exponential. So it means the whole top of this thing is factorial. What about the bottom? What does the cosine of n do? It just flops around between -1 and 1. It can't do it. It's bounded, right? Bounded functions basically contribute nothing to a series. They're bounded, right? They can't get anywhere. Whereas the 3 to the n, well, that's another exponential. So an exponential times a bounded piece is exponential. So what's the limit as n goes to infinity of the inside of this? It's got to be infinity, right? You have something going to infinity like a factorial on top, something going to infinity like an exponential and on bottom. The limit of those terms is infinity. Again, this is what I mean by being able to do a growth, like a order of growth analysis here. The limit as n goes to infinity, n factorial 2 to the n over 3 to the n cosine n is infinity. So does that series converge or diverge? Well, it's not 0, but diverges by the test for divergence. That's all you'd say, because an does not go to 0. This is why math professors like these questions. Okay? Like, were you paying attention? All right. That is the test for divergence. All right, so the last thing I wanted to talk about, sorry, questions about this. This is, you can think about this as being a quick way of triaging series that you're looking at. If you look at a series and it doesn't have terms that go to 0, you can just cross those out and say test for divergence. There's guaranteed to be at least one of those on an exam, right? In the same way that maybe you had a professor like me that told in Calculus 2 that said, there will be an integral that's improper on this exam, and you have to figure out which one the improper integral was and find it. Same deal. I'm gonna put things on exams that diverge very readily, but if you look at the test for divergence. It's important to be able to sort that. Okay. All right, and then the last thing that I want to talk about with this, I think, actually, let's do this. Let's do this real quick. So I did this in my lecture before. Is there anybody that wants to see, because this is a classic question. Are you guys all comfortable with taking a repeating infinite decimal and turning it into a fraction? I did that in the, is there anybody here that wants to see that? Because it takes like 2 minutes for me to show you how that works. Okay, so I'm going to do one real quick here. So let's pick like kind of a nasty pattern. I don't know, nasty. 1, 2, 3. I did that one already, right? 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, forever. Right? So really secretly, that's an infinite geometric series converging to that number, because this doesn't really mean anything. It means there's a limit going on in the background. the way that you approach a question like this is you break it up into this piece and this piece, and so on. So you decompose it into those chunks. And then the idea is once you have the chunks, you can express them as fractions. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now you could go through the entire rigmarole of putting this, expressing this as a geometric series in sigma notation if you want. You can, but you don't need to. Once you've identified that you've got something where you say, oh man, I know that every time I have one of these repeating decimals, that it turns into a geometric series because we're getting from one place to the next just by putting 3 more zeros in the denominator, which is the same as multiplying by 1,000. So R is 1,000. 1 over 1,000. Every one of these repeating decimal expansions is going to have a ratio that gets you from one piece to the next piece by digit shifting, right? Decimal shifting. What's A? I say this is geometric. What's A?
123.
Yes. And the reason that you know that's A is because you don't have to do any formula shifting. It's just whatever comes first. The easiest way to do it. It's easier to do it this way than from the formulas a lot of times. That's A. A is 123 over 1,000. R is 1 over 1,000. It should be permanently glued in your head, if it hasn't been already, that geometric series add up to A over 1 minus R when they converge. So this, how do I know this converges, by the way? Okay, so the mathematical way of looking at it, the non-intuitive way, sort of from the definition is, it's a geometric series with R less than or between -1 and 1, right? This is geometric series, the ratio is between -1 and 1. Is there a more obvious way that we know it converges? Because it comes from a number. This is the number it adds up to, right? I mean, it adds up to this number. The fact that I can even write this down means that this converges. Okay. 123 over 1,000. Once you've done enough of these questions, they all look the same. Because you know what's going to happen here is you're going to get 999 on the bottom, and the thousands are going to cancel, and you're going to end up with 123 over 999. Now, this simplifies. So let's come to the first point of this class when I get to tell you this. You never have to do arithmetic. Okay? Ever. You get to the bottom of a fraction, and you get this answer, and you think, oh my God, my professor's going to take points away from me if I don't reduce that fraction. No, don't do that. Don't simplify fractions. Don't do algebra and sort like terms unless you need to for computations. Okay? You get to the bottom of an answer and you get this, just leave it. It's cool. I mean, it's awesome if you notice you can divide by 3, but you don't have to. Okay? So that's how those go. And again, don't do arithmetic. It's not what I'm testing you guys on. All right. So I think probably I'm going to end. We're at the end of 11.2. We're not doing quiz next time, but I'm going to do the same thing we did today. We're going to start by looking at homework questions from 11.2. So I would hope that you guys would go home and start working on that so that you come tomorrow to the top of the class with some questions. And then the rest of the time we're going to spend talking about 11.3. I've got one more comment here. Thanks for the lecture. All right, cool. Thanks for showing up on Zoom. If you're out sick, I'm going to do this like the whole rest of the quarter. I'm going to be putting these things on Zoom, okay? And this recording will also be online so you can refer to it later. And then I'll post something that has notes with it as well. So anyway, thanks for coming. It's nice to meet you guys in person. As the quarter goes on, this is going to get more interactive, so I'm not just blasting away for 50 minutes of time, I promise. Okay. All right. See you tomorrow. Sure. Let me stop this recording.